Hello students, in the series of low power VLSI design, today we will discuss another topic, that is power consumption in circuits. Okay, we will discuss this topic from from the book of low power VLSI design. Writer's name is Rabi. Okay, okay. So in this topic we will discuss the low power design at circuit level. So we already know that after the invention of transistor, minimization is continuously occurs. So these so so that the various technology comes into play. Out of them, CMOS technology is one of them. The main advantage of this CMOS technology is that it consumes very low power. Along with that, one more advantage in this technology is that the speed of the circuit, speed of the design that made with CMOS technology is very high. Okay, so in CMOS circuit, the static power dissipation not occur. We already discussed the type of power dissipation. In that we have already discussed that there are basically the two type of power dissipation, that is dynamic power dissipation and static power dissipation. The dynamic power dissipation generates because of the two reasons, or we can say the dynamic power dissipation can also be divided into further two types. One is the power dissipation due to the switching of the transistor, and the second one is the power dissipation due to the short circuit current. Okay, so these are the two reasons to generate the dynamic power. Okay, so in CMOS technology, the power dissipation, the power requirement is very low. But when the miniature is continuously formed, when the new technologies continuously comes into play, so that the number of transistor that used in particular integrated circuit will increases. So when the number of component in any integrated circuit will increases continuously, so because of that, the power dissipation, the power dissipated due to the generation of heat is also increases in integrated circuit. So this is also one of the reason to generate the power dissipation. Okay, so because of that, the CMOS circuit gets a limit of acceptable power dissipation. Okay, so the CMOS circuit get its limit for the acceptable power dissipation. Okay, so in this chapter we will discuss the power consumption. So in this chapter we will discuss the power consumption on circuit level and compare various circuit designing techniques. So first we will discuss the CMOS techniques, and later on we will compare various techniques. Okay, this one is the topic: power consumption in the circuitry. The power dissipation is generated due to the main three reasons. First one is the due to the switching of transistor. The second one is due to the flow of short circuit current, and the third one is due to the leakage current. And because of the flow of leakage current, the static power dissipation occurs, and because of the switching and short circuit current, the dynamic power dissipation occurs. Okay, so in the case of dynamic power dissipation, the short circuit power dissipation plays a very minor role. It means that only 10% of total power is dissipated. Only 10% of total power, 10% of total dynamic power is dissipated due to the short circuit current, and 90% power is dissipated. 90% power is dissipated due to the switching activities. Okay, so the first one is dynamic power dissipation. First one is dynamic power dissipation. We start dynamic power dissipation. We start the explanation of this dynamic power dissipation by taking this first diagram. Here, this diagram represents a inverter circuit by using CMOS technology. In this CMOS technology, we connect a pull-up resistor and pull-down resistor. This pull-up resistor is made with PMOS and the pull-down resistor is made with NMOS. Okay, two capacitors are connected here with a common node O. This one is the node O, this one is the node O. Okay, so two capacitors are connected with the node O. First capacitor is C1 and the second capacitor is C2. The C2 is connected with the C2 capacitor is connected with the VD, and the C1 capacitor is connected with the ground. Okay, so when we are discussing the operation of when we discuss the operation of CMOS, so we know that uh, for the complete operation, first we have to provide the input as 0, and later on we have to provide the input as 1. Okay, so when we provide the input value as 0, in the CMOS inverter, so in that case the PMOS is act as a short circuit, and this NMOS is act as a open circuit, because the condition to operate PMOS is that when the input voltage is less than its threshold voltage, so at that time it will operate. And the condition for operation of NMOS is that when the input voltage is greater than the threshold voltage of NMOS, at that time it works. Okay, it works mean when it works, so it will act as a closed path, and when it not works, so at that time it will act as a open circuit. Okay, so when we provide input as 0, at that time this PMOS act as a short circuit, this NMOS act as a open circuit. So when this condition occurs, so at that time this C1 capacitor is continuously charged, because it found a closed path as VDD, PMOS, C1 and ground. So when we provide input as 0, at that time the C1 is capacitor is charged with a voltage VDD. Okay, so the total charged voltage will be, so that in that case the total charged voltage will be the C1 VDD. Okay, and when we provide the input voltage as 1, so at that time this PMOS act as a open circuit, and this NMOS act as a short circuit. So when this condition occurs, so the capacitor will discharge. Towards the 0. Okay, so the capacitor will discharge towards the 0. Okay, so as a result, we take a total charge of C1 plus C2 VDD from the power supply VDD for a full cycle, and at that time the total energy, it is represented here, and at that time the total energy will be C1 plus C2 into VDD square. Here VDD is the power supply. Okay, it is this expression is for the only one cycle. And if you are dealing with a complete string in that several cycles are there. So if we are dealing the complete cycle, so at that time, if we so that at the if we consider a frequency as f, so that the total power dissipation, so that the total dissipated power p will be, so that total dissipated power p will be f into c1 plus c2 into vdt square. Okay, so when we discuss the synchronous circuit, so it is convenient to relate the power in the term of frequency. Okay, relate the power in the term of frequency, as each node do not change simultaneously. It is mentioned here. It is mentioned here because all the node do not change simultaneously. So we need to introduce a probability factor. Okay, so we need to introduce a probability factor to represent the changes in node, to represent the rise on the fall in the node, rise and the fall voltage in the node. Okay, so this probability, which probability? Just changing probability of any node, changing probability of any node. It is represented as alpha. Okay, so when we consider with this switching factor, it is also known as switching probability. It is also known as switching probability. Okay, so when we represent the overall power dissipation in the terms of this switching probability, so we can represent this total switching probability PD equal to alpha fc cl into vdd whole square. We already discussed that this alpha fc in generalized way, this alpha fc can be represented as simple fc when we consider this probability as 1. When we consider this switching probability alpha as 1, at that time we can represent the total alpha into fc as fc. So when we represent alpha into fc, switching probability into fc into as fc, so the total power dissipation equation will be pd equals to fc into vdd whole square. So often in various books, the power dissipated is represented in the multiplication of frequency, capacitance, and the swing voltage, or we can say the supply voltage VTD. Okay, now uh, here switching probability. What is switching probability? Switching probability is alpha. Switching probability is alpha. So this switching probability represent the change in node voltage. Switching probability represent the change in node voltage. Here, if we represent switching probability alpha as alpha x, so it means that here alpha x is the probability that node has the value of x. And if we represent this alpha as alpha xy, it means that it represents the probability of change the voltage from x to y, or we can say y to x. Okay, during one clock cycle. Okay, so as an example, in a clocked node alpha 01, if we consider the value of x as 0, a value of y as 1, so we can represent this alpha xy as alpha 01. Okay, it alpha 01 means transition from 0 to 1, alpha 10 means transition from 10. So as an example, if a clock node has alpha 01 equals to alpha 10, it means that both probability of getting voltage from 0 to 1 and probability of node voltage that decreases from 1 to 0, both are equals, or we represent it as 1. It means that the node changes from 0 to 1 and from 1 to 0 during each clock period. Okay, so the corresponding power, so that the corresponding power consumption expression will include alpha fc as fc. Okay, so this one is the significance to represent the switching probability here. Okay, this one is the significance to represent the switching probability. Okay, here some numerical values of switching probabilities is given. Here some numerical values of switching probability is given. You can also read this paragraph to understand this, to grasp this, to note this numerical value of switching probability. Okay, now the next term is effective capacitance, because we know that in any MOSFET there are the several capacitance. Some of capacitance already generated due to the body effect, and some capacitance is required to connect from the circuit to take the output. When any external capacitance, when any external load capacitance is required, so it is known as so it is represented as CL. Okay, or if some capacitance is already generated due to the charging and discharging, so it is represented as body capacitance. Here several capacitance are represented, here several capacitance are represented, such as VGS. VGS means the gate to source capacitance, gate to drain capacitance, gate to gate capacitance, bulk capacitance, source capacitance, etc. These all capacitance also played a very important role, very vital role for the power dissipation, because we know that the power dissipation is also related with capacitance. Okay, so if we consider this, suppose I am taking an example of this inverter. So here this C1 and C2, here this C1 and C2 can be represented in the terms of load capacitance. Here this C1 and C2 can be represented in the terms of load capacitance. Okay, so the value of load capacitance CL can be represented as C1 plus C2. It means that the load capacitance is nothing but a summation of the capacitance that is connected from output to VDD and output to ground. Okay, so all these points are mentioned here. One another capacitance is represented here, another capacitance is represented here, or we can say if we are using a Miller's theorem, so we can represent the load capacitance. We can change this circuit in terms of input to output capacitance. We can change this load capacitance in the terms of input to output capacitance. So because of the Miller's theorem, we convert this circuit into this circuits. That's why this capacitance, this input to output capacitance, is known as Miller's capacitance, and it is represented as Cm. It is represented as Cm. Okay, so this Cm, the value of this Cm, the value of this Cm changes from VDD to minus VDD. Okay, it means that the maximum value of this Miller's capacitance will be VDD. Maximum voltage that is stored from this Miller's capacitance is VDD, and the minimum voltage that stores from this Miller's capacitance is minus VDD. Okay, so we can say the overall swing capacitance, overall the changes capacitance, overall the charges that is stored by this capacitance will be 2 cm. Overall the charge that is stored here is 2 cm into VDD. Here cm is the Miller capacitance. Okay, this all is represented here. Here's some value of capacitance is represented here, such as this CD is the drain capacitance, this CGS is the gate to source capacitance, gate to drain capacitance. Okay, all these values are represented here. Okay, now the next one is short circuit power consumption. Next one is short circuit power consumption. Okay, before this topic, all the terms that affect the power dissipation is responsible for dynamic power, and we know that dynamic power dissipation are of two types. One is the power dissipation due to the switching. So all these all the factor that we discussed in today's class till now is related with the switching power dissipation. Now the second power dissipation is short circuit power dissipation, and we know that when this short circuit power consumption, short circuit power dissipation occur, we know that uh, We know that PMOS works when the input voltage is less than the threshold voltage of PMOS, and NMOS works when the input voltage is greater than the threshold voltage of NMOS. Okay, but when the input voltage is lie between the threshold voltage of PMOS and the threshold voltage of NMOS, at that time both the transistor will work simultaneously. Okay, so when both the transistor will work simultaneously, so at that time it generates a short circuit path, and short circuit path from VDD to ground, and because of this short circuit path some current is flown from the VDD to ground. Okay, so when the short circuit current flow from VDD to ground, so because of this short circuit current some power is dissipated in the terms of heat. This power dissipation is known as short circuit power dissipation. It is represented here. Okay, PSC, it means that short circuit power. Here several factors are represented here, such as VTHN means the threshold voltage of NMOS transistor. The second factor, VTHP, is the threshold voltage of PMOS transistor, and the first one, VDD, is the supply voltage. Beta is the some parameter. Beta is the some transistor parameter. Beta is some transistor parameter. Okay, and the tau is the and the tau is the gate delay. Tau is the gate delay. Okay, so to calculate the mathematical expression to calculate the short circuit current is beta upon 12 VDD minus VTHN minus VTHP cube into tau upon T. Okay, so this one is the short circuit power dissipation. Now the next one is static power consumption. Why static power dissipation occur? Why static power consumption occurs? This type of power dissipation is generated due to the leakage current. Okay, so due to the leakage current generates in all the semiconductor devices. And because of this leakage current some power is generated, so consumption occurs, and this power consumption is the known as power dissipation is known as static power consumption. And static power consumption is represented as in the mathematical expression as alpha naught. Alpha naught is the data factor or switching factor. Switching probability. I is the current, leakage current, we can say leakage current. Okay, and VDD is the supply voltage. VDD is the supply voltage. So this one is the mathematical expression for short circuit power dissipation. Okay, now the next is pre-charge circuit. Now what is the mean of pre-charge circuit? We know that pre-charge circuit, we know that our main purpose to design any circuit to minimize the power consumption, to minimize the power dissipation. Okay, so sometime we can use some external circuits, some external elements with the CMOS circuitry to save the transistor. What is the purpose to connect pre-charge circuit? First one is to save the transistor, and the second one is to increase the speed. Okay, so one pre-charge circuit is represented here. Here you can say this one, here this one is the CMOS circuit, but here this one is the CMOS circuit, but with the CMOS circuit one more NMOS is connected here. In that the input is in. Okay, so this one is the example of pre-charge circuit. Why this pre-charge circuit is used? Because of the two reasons. First one is to save the transistor, and the second one is to increase the speed. Okay, so means when the frequency is low. Means the input is the input pulse provide from the high time interval, or we can say the time difference between two pulses are low. Two pulses are very high. So the time difference between the two pulses is very high. Okay, so when the clock is low, so at the time the out when the clock is low means when the input is 0. So when the input is 0, so in the case of inverter, the output will be high. Okay, but when the input is high, but when the input is high, so when input is high, so at that time PMOS act as a off circuit and NMOS act as a on circuit. So at that time the input at that time this below NMOS is act as a short circuit path. So at that time the overall circuit is depends on this NMOS transistor. Okay, so we can say the output is controlled by that particular transistor, that is the precharge element for this circuit. Okay, so the single N transistor connected to the input can be replaced by N net also. Okay, so at that time if we want to calculate the dynamic power dissipation of this pre-charge circuit, so dynamic power dissipation of this pre-charge circuit can be represented by this mathematical expression. And if we represent the value of this switching probability alpha 11 as 1 minus alpha a by 2, so at that time this mathematical expression will changed into this form. Okay, so why we use this extra NMOS here, for when we connect this extra NMOS circuitry with the CMOS circuit, so the overall circuit is known as pre-charge. So the overall circuit will increase, so the speed of this overall circuit will be increased. Also it will save the NMOS transistor. Okay, next term is glitches. We know that uncontrolled output signal transition is known as glitches. It is sometimes it is occurs due to during the transition of input pulse from high to low and from low to high. Okay, here one circuit of CMOS XOR gate is represented here. One CMOS gate is represented here. This small fluctuation is known as glitches. Small changes, or we can say suddenly change in the output, is known as the glitches. It is some kind of noise. It is generally produces due to the mismatch of it is generally produces due to the mismatch of input pulse in the two input side of any circuits. Okay, so one more parameter is here, reduced power swing. We can also reduce the power dissipation by reducing the VDD, by reducing the voltage swing. What is the mean of voltage swing? Voltage swing means the changes of voltage from highest potential to lowest potential. Okay, so here one circuitry is represented. Here you can see two external transistors are connected here. One is NMOS and one is PMOS. PMOS is connected with the upper NMOS is connected with the upper PMOS, and PMOS is connected with the lower NMOS. Why these two NMOS and PMOS are connected here? The main significance to connect these two transistors here is to reduce the voltage, is to reduce the swing voltage. Okay, the upper transistor T1, the upper transistor reduces the voltage swing V2 to V2 minus Vt. Okay, so the upper transistor will reduce the voltage V2 to V2 minus Vt, same as the lower transistor will increase the voltage from V1 to V1 plus Vt. Okay, so the overall changes del V equals to this voltage minus this voltage. So when we subtract the first term into with the second term, so we will get V2 minus V1 minus 2 Vt. Okay, so if we not connected these two transistor here, so that at that time the overall swing voltage will be V2 minus V1. But if we connected these two transistor T1 and T2 here, so at that time the this voltage swing will also reduced with the factor of 2 VTT. Okay, so we know that when this voltage swing is reduced, so automatically the power dissipation will reduced. Okay, so one more here we discussed in the first circuit. Here first circuit, we connect two transistors. This circuit is known as the CMOS circuit with no static power, and the second circuit is known as NMOS circuit with static power consumption. Okay, so in the NMOS circuit, no PMOS transistor is connected. Instead of using PMOS transistor, one extra resistor is connected with the circuit. Okay, so instead of using PMOS, we use external load resistor. So because we have not used a PMOS transistor, so this type of technology is known as NMOS technology. In this NMOS transistor, in this NMOS inverter circuit, we use some extra NMOS connected here. This one is I naught, and because of we use NMOS, and because of this NMOS, one current is flow, that is known as I naught, and that current is known as I naught. And because of this I naught, some static power dissipation comes into play, and at that time this static power dissipation is represented by the mathematical expression Ps equals to alpha naught I naught into VDD. Okay, so when we consider the delay, TDD, when we consider the delay TD, when we consider the delay TD, so at that time the overall power dissipation in this delay can be represented as alpha naught CL VDD into this swing voltage. So these all are the low power design, uh, these all are the low power design and circuit level. So in next lecture we will discuss the flip flop and latches. Okay.